yeah, like we were not getting current values. I'm like, well, we have a voltage going through it. Why no current?
Oh.
And then I was trying to brainstorm why, and then I took it out. I'm like, oh, there's no current for it to
Oh.
for the voltage to go through. The travel.
Yeah, I have made some comment here, but I think
Okay, good.
the things like this. So first is leaves, right? And suppose this is so that's this R2, R1. And at this position, there is comment basically right? So at this position, because R2 top is here, right? So we have only the velocity is tangent. We see that, only see that part, right? And see the part.
Right. Okay.
Yeah,
Yeah.
I think that is, and then you use this, the conservation of
Yeah,
the moment,
okay.
right? So,
Okay.
yeah. And another thing is really make, from here, I think, sorry. We have also used this condition.
Where it's
Sometimes, yeah, in this case. And then later, you use it. When you have this, you find this, right? Yeah, so we know this, and we have unknown this, but we can use this.
Are you ready?
What is in the after that is the polybar,
Yeah.
so the energy is 0, and we have some n r2 square minus r2.
Today turn the light.
This is the
I will
kinetic energy plus also kinetic
camera
energy, right? So
and
we
post
have
it on the disk.
the radio part.
If you like.
Radio part. Or just right. I think we do
Sometime?
just kinetic
Many
plus
times.
potential.
You did that?
Yeah.
You look so busy nowadays.
I agree.
Yeah, and then you stop you here, so then the only the unknown is this one.
Okay.
So you just PR is the compound.
Okay. Cool.
So I think one thing is this one, another is this one.
Okay.
Yeah, okay. I make some notes, but not like this, so I just want to. Okay, that helped you.
Yeah.
Okay.
Yeah, thank you.
Good, good.
Was it good?
Yeah, it was good. You took that?
Homework 4.
I'm planning to
I only assigned 2 problems, chapter 8. That's
I
2.
can get it for you. I will take it.
Chapter 3.
Yeah.
E1 and E14. You next Thursday. So I think 2 problem is okay this weekend. Yeah. All right. So now let's keep continue. Yes.
No.
I can show you after the
Last time we
Don't
discussed one
Okay, let's close the chapter.
example is we have a 2 particles. Connect with a spring here, and the center of mass is moving in this constant velocity and 2, right? So we define this one is x, distance between the 2, and center of mass. So we use the general coordinates, which is x, c, center of mass, and x is the relative distance. Then we build up, write down this Lagrangian. Just remind you, can we keep doing this? I think we will finish chapter 8 and start chapter 9 today. So, my Lagrangian is a function of x, center of mass, relative the distance between 2 particles. Then this general speed and heat in general, right? So that is kinetic energy minus potential energy, and kinetic energy we have two terms, right? Center mass and then the relative. So center mass is m1 plus m2 hcm dot square, right? And the relative we use the reduced mass. And potential is only considered the elastic potential half of A x minus L squared. Okay, I think when we have this, now we are going to apply the Hamilton's equation of motion, right? So we first need to construct Hamilton from here. X minus L, right? That is this one. Okay, so here, x dot cn, pcn plus x dot p minus half of m1 plus m2 xcn dot square minus half of a x dot c plus half k x minus L. So now we are going to remove or replace xcm dot and x dot in terms of pcm and p, right? So that is how to construct Hamiltonian. Then we know pcm is partial L partial xcm dot, right? So now we do that. That is m1 plus m2. So from here, we can immediately get this CM dot is M1 plus M2 over PCM. Similarly, P is partial L, partial X dot. And that is here, right? The X dot that is mu X dot. And the X dot is P over mu. So we have Hamiltonian. Now let's do that. So we have PCM, M1 plus M2, this one and multiply PCM, plus P over mu multiply P, minus half of M1 plus M2, and then this is a PCM over M1 plus M2 square, minus half mu P over mu square and plus half K x minus L square. Then this term we can have combined together is become finally half of M1 plus M2 PCM square. This one and this one is plus half of mu P square and plus half of. Okay, here you can also double check this. Since L, if you look here, this is a project term, this is also project term. This is zeroth order of velocity, right? So that is L2 minus L naught, plus L naught. And L2 is nothing but T, right? Because this is a kinetic energy plus L naught. Because L1 is equal to 0, right? And L naught equal to minus V. So we know the H is equal to E, right? We have these two conditions. And this means, similar means partial R, and this is equivalent to partial R and partial T equal to 0 and Fi equal to minus, right? Equivalent. So you either look at this two or look at this, right? And also, since partial L, partial T, partial H, partial T equal to total time period of H equal to 0, so H equal to energy and it is constant. In this case, energy is conserved. Okay, so this is the way I teach, let you know there are two ways to construct Hamiltonian, right? This is the first type. Alternately, I also want to do some practice. so you are familiar with. Another way is matrix, right? H is half of P transport A transport, P inverse and P minus A. This is column matrix minus L naught, right? And here A is 0 since we have no L1, right? So this linear function of this general velocity is 0, coefficient 0. So, and then that is 1, then T. This is a 2 matrix because we have 2 variables, right? So that is a matrix column or 2 by 2. The first one is this, you see here, we have this term and this term, right? So we have T is M1 plus M2, 0, 0, mu. So T1, T inverse is this. Right? So now we can construct H very easily. Half of P, in this case, P is column matrix, and this transport is a row, right? So that the PCM, P 2 dimension, right? Because A is 0, so that is. And then the T inverse is 1 over M1 plus M2, 0, 0, 1 mu, and PCM, P. Minus L naught is this one, right? L naught is minus, so minus became plus. Then you do this one, this is equivalent to this. Sorry. It's equivalent to this. Right? Okay, put that back down. So same as this one. Half of, if you multiply, this one not this one, and that is PCM square over M1 plus M2, half of P square over mu, and plus half of A x minus A. Same as this one. But another way, so it's really depends which one you prefer. Okay, so once we have Hamiltonian, we can solve by apply this Hamilton's equation of motion, or we call the canonical equation of Hamiltonian. So Hamilton's equation of motion, or we call the canonical equation of Hamilton. So that is, okay. Q dot, right? Q dot, first Q dot is XCM dot is equal to partial H, partial P, right? Correspond to PCM, right? This one. Second one, X dot is partial X, partial P. Number 3 is PC M dot is negative partial H, partial XCM, and the last one, P dot is negative partial H, partial X. Right? 4 equations because we have 4 canonical variables. Then now let's look at the first term. So you can see here, when we do the partial H, partial CM, so we can equal to PCM M1 plus which is 3 naught, right? Which is nothing but the velocity, center of mass velocity keep constant. That is the initial situation to give us. So that is constant. Okay. Second one. Okay, let me do this. This one because this one is also. See here. Either this one or this one. There's no XCM. That is cyclic, right? The Hamiltonian does not include this. So XCM is the cyclic, right? That is 0. And this immediately give us this center of mass. The linear momentum of center of mass is constant, and that makes sense because we consider, right? This is this one. Divided by this V naught, and this equal to M1 plus M2 V naught, right? So yes, consider. So we get these two. If you know this one, this is about, so from here very easily plus x naught c, and if initially what is the initial position, right? So we get these two solutions, this one, this one. Now we come to here. This one is partial p here. Partial p will have a p over mu, right? Then you give us equation 1, since the other two we don't need to do the furthest. And this one, x is this guy, right? So we have a k x minus L. Oh, I have a minus here. Well, we have minus that here. So that is equation 2. Okay, now we are going to solve this two. So for example, let's just do this. X double dot is equal to p dot over mu, right? From 1. We just do the derivative both sides. And then 2, okay, if this is 3, so now we have a subject 2 to 3. Here, p dot we have, so x double dot equal to minus k x minus L over mu. Okay, so then the remaining part very easy is if we assume x prime is x minus L, so x prime double dot equal to x double dot, then you have x prime double dot plus k over mu x prime equal to 0. So x prime is a kind of a sinusoidal function, cosine omega t. Omega is square root of k over mu. Then x is a cosine omega t plus q, right? Okay, then we can go back to C. So here, then if this is a solution, we are going to give a equation 4. So there's a 4 go to 2. Then the p dot is minus k here, a cosine omega t plus L minus L, right? Here we have a minus L. Okay, let me use this. Then the p dot is minus ka cosine omega t. Then we do the derivative, do the integral because this is a t dp dt, right? This is the time only depend on time, so the p is minus ka over omega sine omega t if plus the initial momentum, relative momentum of this, the relative motion of these two particles. So you see, we effect yourself, right? We first get them. Actually, you can, if you do this derivative, it is nothing but this one, right? Wait a moment. Do cosine omega. Okay, yes. We have this is t. This is we have a mu, right? So that is. Okay. So this gives you another example how to apply the Hamiltonian and canonical equation of Hamilton to deal with the mechanical problems. So we finished chapter, end of chapter 8, there are another two. Okay, go very quick. This is a two idea, or the first is the Lewis procedure that is solve the problem, a mechanical problem. You can use Lagrange equation of motion and canonical equation of Hamilton, and he just combined these two together. So build up a so-called Routh procedure. The Routh procedure is like this. If we have how many Qj from S plus 1 to N, which are cyclic. So if we have several general coordinates cyclic, we give this index is from s plus 1 to n. So 1 to s is non-cyclic, right? So in this case, then we know L is Q1 to QS, right? And there's no from so that the P, sorry. There's no Q when S, QS plus 1 because it's cyclic. And Q1 dot, QS dot, QS plus 1 dot. We have a Q dot. Okay, that is the Lagrangian. And or we can rewrite like this. We separate with cyclic Lagrangian is only the QS plus 1 dot, QN dot, and the return. And the remaining part is non-cyclic, which is a Q1 to QS, Q1 dot, QS dot, and T. So if we can write or separate this, okay. Okay. Then here, define or introduce, that's introduce. So introduce another function we call the loose function, R, which is combination of this here. This is like a Hamiltonian, so Pj, Qj dot, but it is only from the cyclic term. So J from S plus 1 to N, not from 1 to N. So we just sum over all the products of Pj, Qj dot is if Qj are cyclic, then minus L. This L is total, right? So that equal to equal to, I'm going to, here this is from S plus 1 to N, Pj, Qj dot, minus L, cyclic. Cyclic is a function of only Q S plus 1 dot, Q n dot T, and minus the remaining part is non-cyclic. Q1, Qs, Q1 dot, Qs dot T. So you may ask why we construct R. This is just classify or kind of classify into two parts. For one, only deal with the cyclic coordinates, another deal with non-cyclic coordinates by separate. So if we do this, you can see here this part. You see, this part is only deal with this cyclic coordinates. This is a product for all the cyclic coordinates and the Pj and Qj dot, and this is only Qj dot for cyclic. So this one is nothing but Hamiltonian, given by cyclic coordinates, right? This part. And the remaining is now cyclic Q1, Qs, Q1 dot, Qs dot. Now here, if this is cyclic, okay, space. I use the space here. H, cyclic, which is Qs plus 1, Qn, Ps plus 1, Pn. Actually, because they are cyclic, so they are only Ps plus 1, Ps plus 2, Pn, P, right? Since those are cyclic. If cyclic in the Lagrangian, also cyclic in the Hamiltonian. We already discussed before, right? So now you can see the Hamiltonian, cyclic Hamiltonian only function of P, and the non-cyclic Lagrangian is function of Q and Q dot, but only from 1 to S. Okay, once we have this, now let's look this. So now we can look for non-cyclic coordinates. Now we are going to look this one. Partial R, partial QJ. So J from 1 to S, right? That is a non-cyclic. Partial R, partial J. And then you can see here, this does not include. So only this one, right? So that is only equal to negative partial L, non-cyclic partial QJ. Okay, then partial R, partial QJ dot is here. Also, there's no QJ dot here, right? Only this one. So that is also negative partial L, non-cyclic partial QJ dot. Okay, if we combine these two together, what you can see, they form this equation motion is nothing but equation, Lagrange equation motion for the non-cyclic. So now dr, so we combine together, then let's see this one. Total time derivative of partial r, partial qj dot minus partial r, partial qj. That's equal to this one. So that is total time derivative of partial non-cyclic partial qj dot minus, I think here you have a minus. Okay. Minus here, right? But all are minuses you can see that you can use. And minus partial non-cyclic partial qj. And that's equal to negative d dt partial L non-cyclic partial qj dot minus partial L non-cyclic partial qj. This one follows the Lagrange equation, right? Because it's Lagrange. It's only for the general coordinates which is not cyclic. So that's equal to 0, right? Then that means this equal to 0. So now what you need is, when we build up this Roos function, then what we found for non-cyclic coordinates, actually, when you do this equation motion, it's nothing but just this. So you just do this and equivalent to this. That is for the non-cyclic. For cyclic, so J from S plus 1 to N, right? Then now let's look at this. Partial R, partial QJ is equal to, okay, here. Does not include QJ, right? This is a cyclic. So not include, then only this term. But this term also does not include, right? So, okay. Oh, wait, sorry. Let me do this way. Partial H, cyclic, partial QJ. Because this term is 0, so that's equal to, because this term is equation here. This is a Lagrange equation. This one is canonical. One of canonical equation of Hamilton's, right? So here, yeah, we just do this. Partial this. And of course, if 0, then that means it's a constant. That makes sense. So because it's 0, right? And this is constant, right? So, but I just keep here. This is just general. And partial R, partial PJ. No PJ here, only here, right? Of course, this is for this J from S plus 1. So that equal to partial H, cyclic, partial PJ, immediately. So that is nothing but according to the canonical equation of Hamilton, that is Q J dot. So, I mean, nothing's new. This is just the way how to, if you want to take this procedure. But if you just prefer, like, just consider the Hamiltonian and the canonical equation of Hamilton, that is also fine. So I think this one doesn't give us anything, the new concept, or just some new way to deal with the equation, or some new deal with the system. Now the last simple discussion is a variational principle. Remember in chapter 2, we use the variational principle. We applied variational rule. Right? How to do that? We say that apply the variational principle not equal to 0, and then derive to the Lagrange equation, right? That is, so now, here, this is so now in chapter 8, we are going to apply this variational principle again to derive this one, derive the equation or canonical equation of Hamilton. So we're going to apply again to derive Qj dot equal to partial H, partial Pj, Pj dot is negative partial H, partial Pj. We are going to derive this. Okay, so how to do that is also very simple. This is a variational principle. Now, this is for L, here we for H, right? So now because H equal to summation Pj dot minus L. So the L is just minus H, right? I just move L to the right hand side, move H to the right hand side. Then I substitute L here. Because Lagrange follow this, yes.
Well, I have a question for a variational principle. Because in quantum mechanics, there is also a variational principle. Are they the same or no?
Okay, variational principle's idea is when we do remember we derive this is a derivative from this actual path, various infinitesimal deviation of the path, then if this physics, there's a stable, so this deviation should be 0. That is just an idea. The variational principle is idea if we have, suppose there is a stable states, and any stable deviation from the stable states, that these deviations will go to 0, any path. But quantum mechanics is similar way. They just do this energy and do the partial energy that's equal to 0. Then you can get the Planck states.
Okay. So
Yeah,
we should-
the idea is the same.
Yeah, that's right.
Yeah.
Okay. Thank you.
Okay, so now since L is this, so we can substitute here. This L now is summation Pj dot minus L T minus H, sorry. It's equal to 0, right? After I apply. Then now you can see here, okay, so I mean, if remember we use the Euler Lagrange-Euler equation. So this is a function. Now this function is function of here Hamiltonian. Let me write down details. Hamiltonian is a function of Qj, Pj, and T, right? That's equal to 0. And here, so you can see this. If I consider this as a whole function, this function of Qj dot, Pj, and Pj. Okay, even though we do not have Pj, but we just derive as a Pj dot. This is it's a function to consider all the, because you consider this time change, this increase goes back to time, right? So that is kind of, in general, this be a function of these four variables. Then if this case, so we just use the Euler Lagrange equation, which we discussed in chapter 2. So the details we will not do, right? So then you remember that this gave us, if that is the case, then we have d dt partial f partial qj dot minus partial f partial qj equal to 0, since this is a pair, right? Another is this pair, but pj is just the derivative. So we have a second equation is partial f partial pj minus partial f pj dot partial f partial pj is equal to 0. You just consider those are our variables. In the Euler's Lagrange equation, we have x and y. Remember, y is a dx. The parameter y function is df dx, that is y, right? Same thing like this. So, but in this case, we have this j from 1 to n. We have this pair and this pair. And then for each one, follow this. And then let's see, these two type equation can give us the result is very interesting. Okay. Let's first look at partial f, partial qj. Is only this one has qj, right? It's negative partial h, partial qj, right? That is one thing. And then partial f, partial qj dot. Only this term, no qj dot here. So that is pj. Okay. Then you sub these two into this folder. So what you have? So, okay, I'm just right now here. So this means here d is pj, right? So that's pj dot, right? And minus this one plus partial f h partial qj equal to 0 or pj dot equal to negative partial h partial qj. That is one of these canonical equation, right? Of Hamilton. So that is first one. Now that is from first equation you get this one. And from second equation we can also get another one. So then partial f partial pj. We're going to look at this one. Partial f is here and here, right? So that's equal to qj dot minus partial h partial pj, right? Then partial f partial pj dot is 0. No pj dot here, right? So we substitute these two into this equation here. Then this is 0 equal to negative qj dot plus partial h partial pj equal to 0. Then that is qj dot equal to partial h partial pj. See, this two equation is canonical equation of transmission of Hamiltonian, right? So that is again we can apply the variational principle by this principle. We have followed that we proved in chapter 2, right? What we did is just replace L in terms of this h. Then this became another function, so we applied the Euler Lagrange equation. We can quickly do this one. Okay, so chapter 8 we finished, and the goal of chapter 8 we introduce Hamiltonian. We introduce Hamiltonian and we derive this canonical equation of Hamilton or Hamilton equation. This in another way to solve the mechanical problem, right? So now, why we introduce Hamiltonian in chapter 8? We already introduced Lagrange in chapter 1 and 2, and we solved the system mechanical problem is successful. Why we go to this one? At the beginning of chapter 8, we already say that we want to reduce the second order differential equation to first order, right? That is the first goal. Actually, that is not the only one. The more important Hamiltonian, we have advantage. Pages of we introduce Hamiltonian's formulation. Leibniz, there are more advantage. Leibniz. First, here, these two sides, right, is independent. Then that reduce this, the equation motion became a first order, right? Minus h h qg. That is the first order differential equation. That is the first. Second one. This first seems like a kind of tool to apply to deal with or solve the mechanical problem from the Lagrange equation to the equation of Hamilton. But this is not the only tool. This also offer the deep insight of the concept or content of a mechanical problem or system. What that means? Here, in the later on, you will see this is these two equations. It gives us not only deal with the mechanical problem, it also gives us some of how about the role played in the system, and this will give us the fundamental idea or fundamental concept about the system. So that is over. That gives us basic or fundamental. Ideas or concepts for the mechanical system, and also can extend to the modern physics. This modern physics idea all come from here, like static mechanics, and the quantum mechanics. Since remember the quantum mechanics, you almost learn quantum mechanics, we introduce this one, right? And this operator on this one, and the idea, and also some of the commutator relation between, for example, any time derivative of operator, excitation operator is something like this one, right? Plus partial t. Or you solve the Schrodinger equation, time independent Schrodinger equation, or time dependent. All we introduced here, and that's idea come from Hamiltonian. This come from the Poisson bracket, which we are going to discuss in the end of chapter 9. So you see, this is the and in the statics mechanics, we need the partition function. The partition function need energy, and that energy in classical it is energy. In the quantum mechanics statistic, it is Hamiltonian. So the Hamiltonian is a kind of point departure from here to the other modern physics. So okay, so that is why we are interested on the Hamiltonian. But now, in our class, okay, we know that's important, but we also want to go to the details of how to deal with this here. Okay, in initially this idea is, or the goal is, or motivation is good, that we try to reduce the order of the differential equation, yes. But practically, to solve this one, it is not easy. Okay, so you see here, there's a Q dot is partial H, partial PJ, but it is again a function of QJ, PJ, T, include O in principle. It is, this is a cross term. You cannot, in general Hamilton, you cannot distinguish or separate each term. So that is still function of Qj, Pj, T, and J from 1 to n. Cross terms makes this difficult. To solve. Again, even though we reduce the order of differential equation, but still not yet has a general way to solve it. So because we have a cross term here. Then the remaining part in this class is try to find a way, discuss in general way how to deal with. We are going to introduce the scheme. So the scheme is come from this idea. Then the question is how to solve it, right? Okay, let's consider first, consider this case. Then that is idea, consider if we have Qj is cyclic. The reason why we're always interested in cyclic, you will see that it's very important and a very good feature to deal with the system. If this is cyclic, that means Hamiltonian is function Q1 to Qj minus 1, Qj plus 1, Qn, P1, Pj, Pn, T, right? Here needs to be Qj. Then if this case, then we know Pj dot, according to the canonical term here, right? Pj dot minus partial H, partial Qj is 0 since H does not consider Qj. Then immediately got the Pj, and Pj is constant, right? I'm going to use alpha j. So what does it mean? Initially, we have to deal with 2n first order differential equation. But if there's one cyclic, at least one equation here for Pj immediately got a constant. So that is reduced if we, that at least reduce one of the equations we don't need to solve, right? It becomes simple. So that means we reduce the number of equations to be solved. Right? So that is the case if that happens. And even that, okay, I think later you will see that. So that means that is if there's one, at least reduced so that solved from 2n to 2n minus 1, right? At least reduce 1. Then next, okay, if all the general coordinates are cyclic, that all the general the conjugate momentum is constant, then we reduce from 2n become n, right? So that is good, but you may ask a question, is that possible? Yes. We try to see if it is possible or not, right? So that is the idea. Okay. Now, this is consider if, second if, if all are cyclic. It is possible, let's see if it is possible. But suppose if it is all cyclic, then what happens? the Hamiltonian is only a function of, conjugate momentum, right? P1, Pn, T. And because Pji is, Pj dot is partial and partial Qj is 0, so all the Pj is constant. Then we are going to say alpha j. So Hamiltonian is only the function of all the constant, alpha 1, alpha n, t. Right, because alpha all constant. Then, second then, Qj dot, partial h, partial Pj, right? This one. We already saw Pj dot because it's constant since it's cyclic. Now look at the Qj dot. Qj dot is also interesting because partial h, which is partial alpha j, right? Okay. And it is function of alpha 1, alpha n, t, right, in general. Because whatever you do the partial is, again, only function. Since Hamiltonian function alpha, no q, then the Qj dot is also. Then, okay, that is this case. Now, furthermore, if the Hamiltonian does not depend on time explicitly, then here, the Hamiltonian is equal to only function of r alpha, n. No t. Then what happens? Okay, so Qj dot is partial h, partial alpha j, actually is only function of constant. No t here, right? So if the dqj dt equal to some constant, we can easily integral get the Qj. Qj is now since this is a velocity usually we introduce, it is again this function does not depend on time, right? Because it doesn't. So I'm going to say it's the omega j, which is function of alpha, right? Then I do the integral with respect to the dt. So here, since it's constant, is omega j, alpha 1, alpha n, t plus constant initial position, beta j. So this one is linear in time. We can get this very easily, get the solution. So you can see here, if all are cyclic, we can obtain the momentum is constant. We can obtain this general coordinates is linear in time t. We got solve this solution, right? So, let me just summarize. The solution is Qj is omega j, alpha j, just alpha j, and Pj is alpha j. So that is solution, right? So that means if the system or the general coordinates are cyclic, we can easily solve the solution. Now the question is, can we find all are cyclic? Is that possible? Now the question here is that possible to let all these general coordinates are cyclic? The answer is yes. Why? Okay, why? Because you know the Hamiltonian, remember we said that what the property of Hamiltonian? It depends on the choice of general coordinates. Remember, when we change the sign of general coordinate, the Hamiltonian will change. So if we can select a set of general coordinates such that it becomes cyclic, because it's dependent on this. So it is possible, right? Possible to select a site of such that let's see example. Not the whole sector, but at least we can see if we change the general code. Example, a central force problem, right? Central force. Say the force is just a inverse square root minus k over say like this, a particle, right? So in this case, now the Lagrangian is kinetic energy minus potential energy. Kinetic energy is just consider we have only one particle. Oh, sorry. If we select general coordinates, just the Cartesian x and y. Since we know it's a planar, right? So if we select this, so kinetic energy is this one, right? And potential is minus plus k over this potential is minus k over r, right? So that is r is x squared plus y squared. Then about the Hamiltonian, actually you don't need Hamiltonian, you just look this Lagrangian. If Lagrangian does not have any separate coordinates and Hamiltonian also, right? So, okay. No segment, right? In L. So, definitely there's no. If no, we had to follow the same thing, we cannot solve it. Okay, so that means x, that means x, y are not segment. Okay, now if we select general coordinates by the polar coordinates r and theta, then we can rewrite that Lagrangian is half the Lagrangian in this in the polar matrix is r dot square plus r square theta dot square, right? And minus k over r, plus k over r. So this is plus because minus 3 plus. So here, you can, here already we know the theta is separate, right? No theta. And if you convert to the Hamiltonian, that is from here to here, I just directly give the result since it's very simple. You can do yourself. Construct Hamiltonian from the Lagrangian. So you see here also r, Hamiltonian only function r dot, and theta dot, no theta. So theta also separate. Then we can immediately got this p theta to be constant. If we say that is r dot theta, then this this constant is theta dot is partial h, partial p, theta is partial h, partial alpha theta, and here this is 2, so that is p theta over 2 over m r squared over alpha theta m r squared. So you can see this example, if we try to select different side of general coordinates, indeed, we can make some of coordinates, general coordinates separate. So the answer is possible. The question is, all these general coordinates are separate. It is possible? No, that need the technique we are going to discuss. Okay. So now, go to transform to a new one. Now we consider a Hamiltonian, right? Now to the new one, I'm going to use it such that cyclic. So it's all the new general coordinates are cyclic. How to do that? So we are going to use this. We are introducing canonical transformation. That is chapter 9. Canonical transformation. Okay. That is the purpose of chapter 9. Okay. Now, that means it tells us there is a technique called the canonical transformation. Using this transformation, we can transform this general coordinate to a new general coordinate such that a new general coordinate, all the general coordinates are cyclic. Now, how to do that? So, ideas like this, or idea, or foundation to make this transformation. Okay, first, suppose it's a new, right? New general coordinate is a function of old one. This one also called first, and the new conjugate momentum is also function of old general coordinates and conjugate momentum time. So those are must be point transformation. Second, okay, the new general coordinate must be canonical variable. What does means canonical variables? That means they follow this. Okay, so they follow. Suppose K is a function of general coordinates, a new general coordinates, a conjugate momentum, then the Qj dot, capital Qj dot will be partial K, partial capital Pj. That means follow this canonical equation of motion, equation of the Hamiltonian. So that means when we select or make transformations from an old one to new one, such new general coordinates we follow this. That means this is a kind of a new Hamiltonian from the old one transferred to the new one, right? So the old one we already know. Okay, I think that's enough. Old one, the Qj. Those are canonical variables since they follow this the equation for Hamiltonian partial lower p, partial h, partial lower q, right? So that is already followed. Now the question asks that when we transform the new one, they also follow this. So that is second question, second condition. Third one, this transformation technique to be independent any specific system of specific system. That means if only apply to some specific system, does not apply to any arbitrary system, it is not the canonical transformation. We have asked the transformation such that this apply to those. For example, okay, we have a 2D harmonic oscillator. Harmonic oscillator. Or 2D Kepler's. Form. They are different systems, right? But they are all 2D. So these transformations will hold true for all cases. They must be hold the same. That means if we transform, make a canonical transformation from an old to new one, which apply to the 2D harmonic oscillator, as also follow can apply to this. So that makes this canonical transformation more general. That is required. And how to satisfy this? How to satisfy this is there's a general technique. Okay. Now the question is how to perform, how to realize or perform. All right. Let's view from here. Consider. This variational principle, or we call that we have the variational principle from this. Okay, del dt equals to delta qj dot minus h. Right from here. So we know this, I just discussed before, right, at the end of chapter 8. Because this, consider this. And this one, we just proved that this will derive to the Hamiltonian as a function of Qj, Pj here, and then they follow this, canonical variable because they follow this canonical equation of Hamilton. Pg dot is minus h partial Pg, right? That is from here. So now, if we want to make the canonical transformation from the old Jericho to the new ones will follow the same thing. So we give the same. Okay, that is considered. So this is the old, right? Now new is that suppose we have a new is k. Okay, old Hamiltonian. So now we are going to use this, apply here. If this is canonical, then this one, mu, I use capital P, capital Qj dot, minus k. K, which is the transform new Hamiltonian in the new general coordinates. Here also give us k is a function of your general coordinates, general momentum. Then the Qj dot, if this canonical variables, we follow the canonical equation of Hamilton's, so that is partial k, partial p, capital Pg, and the capital Pg dot is negative partial k, partial capital Pg. This is the new. So that is required. If we have this, we are going to make this canonical be satisfied, then must be have this. So we use this relation, then very easily we can set up the relation between old and new. And that gives us an idea how to transform. So because this variation both are 0, then the integral of this be just equal with the sum of unit, right? So because this, you see here, this equal to 0, this also equal to 0. So both this left-hand side, the right-hand side equal to 0, so that means the left-hand side inside this integral is equivalent in certain linear scale, right? So only because that's so, I just say, therefore we have this relation. Lambda, this integrand, right? The integrand relation between two integrands be followed. Minus the old Hamiltonian, which is general coordinates conjugate moment T equal to the new one, summation capital J, capital Q dot minus K, which is function of capital QJ, capital PJ and T. And here, plus total time derivative of this is the key. That means if the integral is this, you put into here, you get 0, and that equivalent I put here, put into integral, the differential, the partial, the variation. So that means they have this relation. Now here, F arbitrary. I didn't have any special. So that is arbitrary, but we have asked this condition for this F. F, any function of the space, that means phase space, so that means variables, function of general coordinates and conjugate momentum. Then this continuous up to the second order. At least we need a total time derivative right here. And it is a function of mixed old and new canonical variables. That's the only required. Because this freedom, so that makes us a different way to define F and to make this transformation. Now before that, let's first prove why we add this one is equivalent. So you can see here, okay, this one, the left, because so use this is left hand side, this is right hand side, right? So now let's look at left hand side, right hand side. This they give us left hand side. So we do this variation. So that is lambda J P J Q J dot minus H dt. Since lambda is constant, right? So that is lambda delta, and this integral J P J Q J dot minus H. This term is 0 right here, according to the Hamilton's principle or original principle. So yes, that's equal to 0. Now let's look at the right hand side. If we define this way, we will keep the 0 not. So now let's look at this. The integral summation of a capital PJ, capital QJ dot minus K dt and plus variation of integral of total time derivative of the f dt. Okay, I think here since I didn't use the T1, T2, since that can make this T2. This is between the path from initial to final, right? So the first one is 0, right? Because here, the first one is 0. The second one here, this is a total time derivative. So this integral is just df, right? So that is delta f t2 minus f t1, right? Then t2, t1, they are function. These are constant, not variables. So when you do the derivative, that is 0, right? Okay, so that means yes, if we add another term, the total time derivative of f, into this equation, they still hold true. So that is very important and very good that we can apply, give us most of freedom to design or construct a canonical transformation. Here, the lambda, let's consider lambda 1. Lambda equal 1 case, because lambda is just a parameter or scale factor, some constant. So for lambda not equal to 1, we will discuss later as one example. Okay. So if we select lambda equal to 1, then which we have the equation is this we call canonical transformation. That means if satisfies satisfy this equation, this transformation between the old and new satisfy these conditions, and that's the canonical transformation. Now, okay. So now the key is how to satisfy, right? So the key is how to select f. Because this is arbitrary, right? And this is unknown. We are going to get this one from the cut. So we know this, but we are going to select this one. And f, I erase it, right? That's here, right? F, we call the generating function. Or bridge, because you can see here, equation left-hand side are all functions of old general coordinates. Right-hand side new, how to build up equal. This one becomes here. Here it is. Mix of old and new. That's like a bridge. To bridge the old and new such as satisfy this equation. So on next Tuesday, we are going to discuss how to select this F. There are several ways, and we will give some type, particular type, and that is not limited. There are some more, but let's just consider some of a particular type. And if you know how to do that, you can develop it yourself. All right. So, chapter 9 and 10, the idea, chapter 9 focuses on how to make the canonical transformation. such as the new general coding are separate. And chapter 10, if that is the case, then how to deal with the details. So that is the techniques in this class. I probably will assign the last homework, chapter homework 5 for chapter 9 as practice before you final exam. Okay. Good. Yes.
For the in-class portion of the exam, any take on, I think it'll be nice to just practice older homework and examples we did in class. It'll be a good study, like method.
You mean before the exam? Kind of a starting date, right? You mean? Yeah, that is. We December 6th, I think. Our class is last one, December 1st, I think, right? I don't know. And then December 5th is content last class. Then maybe Tuesday, if you are, we can come here. If there is no class here, and we can just discuss. You have some idea or some questions. Yeah.
Okay.
Good.
Thank you.
Otherwise, oh, sorry.
No, you're fine.
Okay. No, many questions are coming most of the meeting, this is synthetic, so if it is synthetic, I don't know whether it's true.
Yes.